Welcome back, everyone, for another deep dive. This time we're tackling a new topic, in-context identification attention heads. You've given me a stack of research papers on this, and wow, it looks like you're really getting into the weeds of transformer models for your PhD research.
Yeah, it's a pretty hot area right now. There's so much we're still figuring out about how these models actually work, and attention heads seem to be like a key piece of the puzzle.
So for our listeners today,
hmm
what's the goal for this deep dive? What should they be walking away with?
Well, we're going to break down how these special attention heads work, what makes them tick, and why everyone in the NLP community is so excited about them.
Okay, let's unpack this then. The first paper you gave me is Analyzing Multi-Head Self-Attention. Specialized heads do the heavy lifting, the rest can be pruned. So what's the big takeaway here?
Well, this paper basically challenges the idea that all attention heads are equally important, to a model's performance. Their research shows that some heads are highly specialized and super important for specific tasks, but others can be removed without really affecting the model's performance. They call the important ones heavy lifters.
So it's kind of like a team where only a few members are actually doing the real work.
Yeah, exactly. And they were even able to identify different types of these specialized heads. For instance, neighboring word heads focus on the words that are right next to the target word.
So those almost sound like a really focused editor, checking for things like grammar and making sure the words flow smoothly.
Yeah, that's a great way to think about it. And then there are syntactic dependency heads, which are even more complex. Those heads have learned to recognize the grammatical connections between words, like subject-verb pairs or noun-adjective pairs.
Wow. So it's like the model has its own internal grammar police, making sure everything is structured correctly.
Yeah, precisely. And this finding leads to some really interesting questions, like if we can just prune most of these heads, why do these models even have so many in the first place? Is it just inefficient design? Or is there something else going on that we're missing?
Yeah, maybe it's like some form of redundancy.
hmm
Or maybe those less important heads actually do have subtle roles that we haven't fully grasped yet. This seems like an area that needs more research.
Yeah.
Okay, the next paper on our list is Adaptively Sparse Transformers. And it talks about this idea of sparse attention. Can you break down what that is and why it matters?
So, in a nutshell, sparse attention means that the attention heads only focus on a few specific words, instead of spreading their attention evenly across all the input words.
Okay, so it's kind of like if you were reading a paper and you just highlighted the key sentences. So
Yeah.
you can get the main idea without having to read every single word.
Exactly. And they achieved the sparsity by using a technique called AntMax. It's basically a more adjustable version of the softmax function, and it gives them more control over how much attention is distributed.
So NetMax basically lets the model learn how much attention to pay to each word.
Yeah, you could see that. It allows for different levels of sparsity depending on the context. And here's what's really interesting. This sparse attention can actually make the model easier to understand.
Really. I would have thought that focusing on fewer words would make it harder to figure out what the model is doing.
I know, it seems kind of counterintuitive. But by zeroing in on the most relevant words, we can actually see more clearly which parts of the input are influencing the model's decisions. They have a really good example in the paper of a head that's really good at merging words that were split up during the byte pair encoding process.
So this head is basically acting like a detective. It's putting the pieces of words back together to get the full meaning.
Yeah, exactly. It shows that the model isn't just processing random tokens, it's actually learning to understand the structure and meaning of language. Now, let's switch gears a bit and talk about this concept of copy suppression. This is something they explored in the paper Copy Suppression, Comprehensively Understanding an Attention Head.
The title itself is intriguing. I'm guessing it has something to do with stopping the model from just repeating words it's seen before.
You got it. They found certain attention heads that they call negative heads that actively try to prevent the model from simply copying words from the earlier parts of the input.
It's like a built-in plagiarism checker, making sure the model is coming up with its own original stuff.
Yeah, that's a good way to put it. And they were able to break down this copy suppression process into 3 steps. The first step is what they call naive copying, which happens in the earlier layers of the model.
So like a rough draft where the model is still just trying to figure things out.
Right, and that's where the negative head comes in. It basically spots this copying behavior and tries to regulate it.
So the negative head is like a quality control expert, making sure the model isn't taking the easy way out.
Exactly. And in the final step, the negative head actually reduces the likelihood of that copied word being chosen. It basically pushes the model to come up with more thoughtful and accurate predictions. What's really remarkable is that the researchers were able to explain almost 80% of how this negative head impacts the model's final output, which is a huge step forward in understanding these complex systems.
Wow, that's a really impressive level of interpretability. It definitely supports the idea that these attention heads are becoming specialized.
Yeah.
They have very specific and critical roles within the whole system. Now let's shift gears again and talk about positional information. Now these heads use it in a task like predicting acronyms. This is something they explored in the paper. How does GPT-2 predict acronyms? Extracting and understanding a circuit via mechanistic interpretability.
So in this research, they really honed in on acronym prediction as a way to understand how GPT-2 Small handles tasks that go beyond just predicting single words. They were extremely careful about how they designed their data set to make sure that it aligned with how GPT-2 processes text.
So they were basically trying to speak the model's language.
Exactly. They were specifically focused on GPT-2's byte pair encoding tokenization, which often breaks words down into smaller units. So they had to make sure that the words and acronyms they used would be tokenized in a way that GPT-2 would encounter naturally.
So they were giving the model a realistic puzzle to solve, making sure the pieces fit together in a way that makes sense to the model.
Yeah, that's a great analogy. Now, in terms of how they analyzed GPT-2's behavior, they used a bunch of techniques that are common in the field of mechanistic interpretability, like activation patching.
And what were they able to find out through that analysis?
Well, they were able to pinpoint some very specific attention heads that were essential for accurately predicting acronyms. They called these heads letter mover heads, and they're responsible for choosing the right letter from each word to form the acronym.
Okay, so each head has a specific job to do,
Yeah.
like workers on an assembly line.
Yeah, exactly. And what's really interesting is how these letter mover heads use positional information to make the right predictions. They found that these heads rely heavily on the attention that's paid to the very beginning of the sentence, which is marked by something called the BOS token.
So the BOS token acts like a reference point.
Mm.
It helps the model understand where each word is located within the sentence.
That's a great way to think about it. And what's even more fascinating is that this positional information seems to be encoded directly within the attention patterns themselves. It's not just about those predefined positional embeddings that are typically used in transformer models.
So the model is learning a more complex and dynamic way to represent position than we originally thought. It's not just using a fixed map. It's actually figuring out the relationships between words based on the attention patterns it learns during training. That's super insightful. Okay, I want to switch gears one more time and go back to the information flow routes paper. They mentioned that their method is not only much faster than the traditional patching circuits approach, but it's also more versatile. Can you give us an example of what that versatility looks like in practice?
Sure. One of the biggest advantages of this information flow routes method is that it can analyze how the flow of information changes depending on what the model is processing or what task it's trying to do. With the traditional patching techniques, you're usually limited to analyzing just one task at a time. But with this method, you can actually compare and contrast how information flows for different inputs or different tasks.
So it's like having a map that can show you different routes depending on where you're trying to go. You can see how the traffic patterns change based on your destination.
Yeah, exactly. For example, you could use this method to analyze how the information flow is different when the model is processing something factual versus when it's dealing with a hypothetical question. Or you could even compare the flow of information across different languages to see how the model changes its processing based on the specific features of each language.
That's really cool. It gives us a whole new level of understanding of how these models work. It's like being able to see the model's thought process in action. You know, how it adapts and changes based on the context.
Oh.
Okay, one last question before we move on to our teaser for the next deep dive. In the Sudden Drops in the Loss paper, they talk about how the timing of releasing the SAS suppression was really important. Can you explain that a little more?
Yeah, that's a really key point. They found that releasing the suppression at the right time was crucial for getting the effect they wanted. If they released it too early before the model had a chance to explore other strategies, it would just go back to relying heavily on SAS, which would basically undo all the benefits of the suppression.
So it's kind of like taking the training wheels off a bike too soon. The kid might fall and just get discouraged.
Exactly. But on the other hand, if they waited too long to release the suppression after the model had already gotten used to a less effective strategy, it would be really hard for it to change course. It would be like a ship that sailed too far in the wrong direction and can't easily turn around.
So it was all about finding the right balance.
Yeah, exactly. They had to find that sweet spot. The moment when the model was ready to try new things, but hadn't gotten too stuck in its old ways.
This really shows how important it is to carefully watch how the model is developing and make adjustments along the way.
Absolutely. It's not a set it and forget it kind of process.
Yeah.
You need to keep a close eye on things and step in at the right times to guide the model towards better learning.
Well, this has been a really insightful look at in-context identification attention heads. We've covered so much ground today, from discovering these specialized heads and the power of sparse attention to the surprising role of copy suppression and the really intricate ways these models use positional information. It's clear that this area of research is moving incredibly fast, and the things we've talked about today could totally change how we understand and interact with language models in the future.
I totally agree. And what's even more exciting is that we're really just scratching the surface here. There's still so many questions we haven't answered and areas we haven't explored yet, like how do these specialized heads actually learn their specific roles? Are there other types of specialized heads out there that we haven't discovered yet? And can we create models that are less prone to this simplicity bias from the very beginning?
Those are great questions. It seems like every answer we find just leads to more interesting questions. It really shows how complex and full of potential these language models are.
For sure. And as these models keep evolving and getting even more sophisticated, our understanding of them needs to keep pace too. It's a constant challenge. But it's also really exciting.
Okay, so to all our PhD student listeners out there,
Yeah.
keep exploring, keep asking questions, and keep pushing the boundaries of knowledge. The world of AI is full of mysteries, just waiting to be discovered.
And we'll be here with you, diving deep into those mysteries and bringing you all the latest insights and findings.
Speaking of mysteries, next time we're going to be exploring the world of latent reasoning. It's a topic that promises to shed some light on the hidden thought processes of AI models. How do they connect seemingly random pieces of information? How do they make inferences and come up with conclusions that aren't explicitly stated in the input?
It's like trying to read the mind of the model.
Exactly. It's a really fascinating and challenging area of research, and we can't wait to explore it with you. So stay tuned for our next deep dive.
Yeah, it really is a bit like being a detective. You know, you're trying to piece together all the clues to figure out how these models get to their conclusions. Before we jump too far ahead, I think it's worth going back to some of those really interesting details we touched on earlier. Like in that analyzing multi-head self-attention paper, remember they talked about those specialized heads, the heavy lifters? Maybe we could unpack those a little more.
Oh yeah, for sure. They mentioned two main types, neighboring word heads and those syntactic dependency heads. Right. Let's start with those neighboring word heads. I guess they seem pretty straightforward. They just focus on the words that are right around a target word.
Yeah, they do. But their function is super important. They're essentially helping the model understand the local context of each word. Think of it this way. These heads are making sure that the subject and verb agree. They're catching those little subtle differences in meaning between nearby words and making sure the whole sentence flows smoothly and is grammatically correct.
So they're not just looking at individual words in isolation. They're actually analyzing how those words relate to each other within their immediate surroundings.
Right, exactly. And then you've got those syntactic dependency heads, which work on a much more complex level. Those heads have actually learned to recognize specific grammatical relationships between words, even if those words aren't right next to each other in the sentence.
Okay, so they're looking at the bigger picture, the whole structure of the sentence, instead of just the local context.
Exactly. They can figure out things like subject-verb pairs, noun-adjective relationships, prepositional phrases, and so on. They're basically like the model's own built-in grammar police, making sure that the sentence is structured in a way that makes sense grammatically.
It's pretty amazing that these models can learn these really complex grammatical relationships all on their own. But how can we be sure that these heads are actually getting it right? Are they accurate in their analysis?
That's a great question, and the researchers definitely thought about that too. They actually used a technique called layer-wise relevance propagation, or LRP, to keep track of how information flows through the model.
So it's kind of like tracing the model's thought process, like following the breadcrumbs to see how it arrived at a particular prediction.
Yeah, exactly. LRP lets them pinpoint which attention heads were the most important in making a specific prediction. And then they compared those predictions to the actual syntactic dependencies in the text.
So basically, they're double-checking the model's work,
I hope so.
seeing if its grammar police are actually doing their job
Whoop.
correctly.
And the results were actually pretty impressive. They found that certain heads were super accurate at identifying specific syntactic dependencies, even in those really complex sentences.
It's really interesting. It seems like these models are developing a much deeper understanding of language than we initially thought. Okay, let's move on to that paper about adaptively sparse transformers. I'm still a little curious about how they actually define and measure this sparsity in attention.
Yeah, so they use this metric called head density to quantify sparsity. Basically, it measures how many of the attention weights assigned by a head are non-zero. So a lower density means the head is focusing on fewer words in the input.
Got it. So a high density means the head is spreading its attention more evenly across the entire input, and a low density means it's zeroing in on just a few specific words.
Exactly. And they found that this adaptive model shows all sorts of different sparsity patterns across the various heads and layers. Some heads are always sparse, they just focus on a handful of words, while others are more dense and spread their attention out more broadly.
So it's not a one-size-fits-all kind of thing. The model actually learns how to adjust its focus depending on the context and the task at hand.
Right, and that's where the IntMax function comes in. Remember, that's that more flexible version of the typical softmax function. And it gives the model the ability to learn the best level of sparsity for each head. Basically, it gets to decide how much information is actually important for making a specific prediction.
So it's like IntMax is a volume knob for attention. The model can fine-tune how much attention it pays to each word.
That's a great way to put it. And this adaptive sparsity actually has some really interesting implications. For one thing, it could potentially make the model more efficient by just focusing on the most important information. And it can also make the model easier to understand, which is pretty cool.
Now that's counterintuitive to me. You would think focusing on fewer words would make it harder to understand what the model is doing, not easier.
I know it seems that way at first, but think about it this way. By concentrating on the most important words, we can see more clearly what parts of the input are actually driving the model's decisions. It's kind of like highlighting the main points in a textbook.
Okay, I see what you mean. By getting rid of all the extra noise, we can get a better picture of how the model is reasoning.
Yeah.
Can you give us a concrete example of how this increased interpretability works in practice?
Yeah, sure. They highlighted a really interesting head in their paper, which they called the BPE merging head. And they found that this head was specifically designed to merge words that had been split up during byte pair encoding, or BPE.
Oh, right. BPE is that technique where they break down words into smaller subword units. So this head is kind of like a word detective. It's putting those word fragments back together to understand the full meaning.
Exactly. And the researchers could actually see this happening by analyzing the head's attention patterns. When it encountered a word that had been split up by BPE, the head would pay really close attention to the subword units that belonged together, basically merging them back into a single meaningful word.
That's so cool. It really shows that the model isn't just blindly processing a bunch of random tokens. It's actually learning to understand the underlying structure and meaning of language. Okay, I want to circle back to that copy suppression paper for a second.
Yeah.
They talked about how those negative heads work to stop the model from just copying words from earlier in the input. Could you walk us through that process in a bit more detail?
Of course. So they found that copy suppression is actually a multi-step process. It's not just the negative head that's involved. It's also got components in the earlier layers of the model. It's kind of a team effort.
So it's not just a single head acting as a plagiarism checker. It's more like a whole team working together.
Yeah, exactly. Think of it this way. The earlier layers of the model are responsible for making those initial predictions based on what they've learned, and sometimes those predictions might involve just copying a word or phrase that they've seen before.
So it's like a first draft where the model is still kind of brainstorming and hasn't refined its ideas yet.
Yeah, a perfect analogy. And that's when the negative head steps in, like a quality control editor. It examines those initial predictions from the earlier layers and looks for places where the model might be relying too much on simple copying.
Okay, so like a built-in plagiarism detector. It's flagging any potential instances of unoriginal content. But how does the negative head actually suppress the probability of that copied token? Does it just like delete it from the model's vocabulary?
No, not quite. It's a little more subtle than that. The negative head actually works by changing the model's internal representation of those predicted tokens. They're called logits. Basically, it adjusts those logits to make the copied token less likely to be chosen as the final prediction.
So it's not erasing the copy token completely. It's just making it less appealing to the model, kind of nudging it towards other, more original choices.
Exactly. And that's really important because it lets the model consider other, more nuanced predictions that might be more accurate and show a deeper understanding of the context.
It's a pretty clever approach. It keeps the model from getting stuck in a rut of just repeating what it's seen before. Now let's switch gears again and talk about that paper on how GPT-2 predicts acronyms. It sounds like they were really careful about how they put together their data set to make sure they were studying how GPT-2 actually behaves.
Hmm.
Can you tell us a bit more about that?
Yeah, they were super meticulous about making sure their data set matched how GPT-2 actually processes language in the real world. They called this staying in distribution. Like I mentioned earlier, they really stuck to GPT-2's specific tokenization scheme, that byte pair encoding, or BPE, which often breaks down words into those smaller units. So that meant they couldn't just use any random combination of words to make acronyms.
So they had to pick words that would be tokenized in a way that GPT-2 would naturally encounter.
Right. They had to make sure that both the words and the acronyms they created would be broken down into those subword units in a way that reflected how GPT-2 actually works. They did this by filtering out any words and acronyms that didn't fit those criteria, so they ended up with a smaller data set, but it was much more relevant to their research.
So it's like they were speaking the model's language,
Right.
using the same building blocks that the model uses to understand language.
Exactly. They didn't want to give the model inputs that it would never see in a real-world situation. By staying in distribution, they could be confident that their findings were actually showing how GPT-2 operates naturally.
That makes a lot of sense. So once they had this carefully crafted data set, how did they figure out how GPT-2 actually predicts acronyms? What kind of techniques did they use?
They used a bunch of different methods that are commonly used in mechanistic interpretability, which is this field that's all about understanding the inner workings of AI models. One of the main techniques they used was something called activation patching.
Activation patching. That sounds pretty interesting. Can you break that down for us?
Sure. So activation patching is basically where you manipulate the activations of different parts of the model to see how those changes affect the output.
Oh, so they're basically tinkering with different parts of the model to see what happens.
Yeah.
Kind of like trying to figure out how a car engine works by taking out different parts and seeing what changes.
Yeah, that's a great analogy. By carefully patching or manipulating different activations within GPT-2, they were able to pinpoint the specific parts that were involved in correctly predicting acronyms.
And those key parts turned out to be those letter mover heads we talked about before, right?
Exactly. Remember, those heads are the ones that specialize in picking the right letter from each word to make the acronym. So for example, if the model is trying to predict the acronym CEO, there are specific letter mover heads that are focused on the C in chief, the E in executive, and the O in officer.
So each head has a very specific job to do, like they're all working together on an assembly line to create the final product.
Exactly. They all work together to make sure that the acronym is formed correctly. But what's really fascinating is how those letter mover heads actually use positional information to make accurate predictions. The researchers found that these heads rely heavily on the attention that's paid to the very beginning of the sentence, which is marked by that BOS token.
Right, we talked about that earlier. The BOS token is like a reference point that helps the model understand the structure of the sentence. But how do those letter mover heads use that information to predict acronyms?
It seems like they use that attention to the BOS token to figure out how far away each word is from the beginning of the sentence. And that distance information is super important for them to accurately pick the right letter for the acronym.
So it's almost like they're using a ruler to measure the distance between the BOS token and each word in the sentence.
That's a very creative way to think about it. And what's even more amazing is that this positional information isn't just stored in those positional embeddings that are usually used in transformer models. It seems like it's actually encoded directly within the attention patterns themselves.
So the model is learning a much more complex and dynamic way to represent position than we originally thought. It's not just relying on a preset map. It's actually figuring out the spatial relationships between words based on the attention patterns it learns during training. That's really insightful. Now I want to shift our focus back to that information flow routes paper for a minute. They were really emphasizing how their method is not just faster than that traditional patching approach, but it's also more versatile. Can you give us a specific example of what that versatility looks like in action?
Sure. One of the really cool things about this information flow routes method is that it can actually analyze how the flow of information changes depending on what the model is looking at or what task it's trying to do. With those traditional patching techniques, you're kind of stuck analyzing just one task at a time. But with this new method, you can actually compare and contrast how information flows for different inputs or even different tasks.
So it's like having a map that can show you different routes depending on where you want to go. You can see how the traffic patterns change based on your destination.
Yeah, exactly. For example, you could use information flow routes to see how differently the information flows when the model is processing a factual statement compared to when it's working on a hypothetical question. Or you could even compare how information flows across different languages and see how the model adjusts its strategies based on the specific quirks of each language.
That's amazing. It really opens up a whole new level of understanding about how these models actually work. It's like being able to peek inside the model's brain and watch its thought process unfold in real time. You know how it adapts and changes based on the context. Okay, last question before we move on to our teaser for the next deep dive. In that sudden drops in the loss paper, they talked about how the timing of releasing that SAS suppression was super important. Can you elaborate on that a bit?
Oh, yeah, that's a really key point. They found that releasing the suppression at just the right moment was essential for getting the results they wanted. If they released it too soon, before the model had a chance to try out other strategies, it would basically just go right back to relying heavily on SAS, which would basically undo all the benefits of suppressing it in the first place.
So it's kind of like taking the training wheels off a bike too early. The kid might just fall over and get discouraged.
Yeah, exactly. But if they waited too long to release the suppression, after the model had already gotten comfortable with a less effective strategy, it would be really tough for it to change course. It'd be like a ship that's sailed way off course and can't turn around
This
easily.
was all about finding that perfect balance.
Exactly. They had to find that sweet spot. The moment when the model was ready to explore new solutions but hadn't gotten too stuck in its old habits.
This really shows how important it is to pay close attention to how the model is developing and make those adjustments at the right time.
Absolutely. It's not a set it and forget it kind of thing. You have to watch things carefully and step in at the right moments to help guide the model toward better learning.
Yeah, it really is a fascinating area, and it's changing so fast. We're going to be looking at all sorts of different approaches and techniques that researchers are using to try to shed some light on this hidden layer of AI thinking. It's kind of like we're trying to decode the model's internal logic, to understand how it connects the dots and reaches conclusions that might not be super obvious just from looking at the input.
It sounds like we're going to be delving into AI psychology,
Yeah.
trying to understand the mind of the machine.
Exactly. We'll be looking at how researchers are using things like probing and concept erasure, even counterfactual analysis, to try and figure out how these models represent knowledge and reason about the world. Wow, that sounds super interesting. I'm already looking forward to diving into those techniques and seeing what kind of insights they can give us. But for now, I think we should wrap up our exploration of in-context identification attention heads. We've covered a ton of ground today, from discovering these specialized heads and the power of sparse attention to that surprising role of copy suppression and all those intricate ways these models use positional information.
It's been quite the journey through some of the most cutting-edge research in NLP. And what's really exciting is that this field is still so young. There's still so many unanswered questions and so much more to explore.
I know, right? It feels like we're just starting to peek behind the curtain and see the complexity of these powerful models. And as these models keep getting better and more sophisticated at this incredible pace, our understanding of them needs to catch up.
Absolutely. That's why this kind of research is so vital. By digging deeper into how these models work, we not only get a better grasp of their functionality, but we also uncover potential biases and limitations that we need to address.
That's a great point. It's not just about pushing the limits of what these models can do. It's also about making sure they're doing it in a way that's fair and reliable and ultimately benefits everyone.
Well said. It's about harnessing the incredible potential of these models while also being mindful of their impact on the world around us.
So to all our PhD student listeners out there, we encourage you to keep exploring, keep asking those tough questions, and keep pushing the boundaries of what we know. The world of AI is a vast and uncharted territory, and there are countless mysteries waiting to be uncovered.
And we'll be right here with you, diving deep into those mysteries and bringing you all the latest breakthroughs and discoveries.
That's right. So until next time, keep up the great work, and we'll see you on our next deep dive into the fascinating world of latent reasoning.